Welcome. This is the lecture for Chapter 15, Market Demand. Okay, the first idea in this chapter is that when you're dealing with more than one person, you're dealing with not an individual's demand, but with market demand, demand of the whole market. You can, roughly speaking, imagine the entire buyer's side of the market as one big person. Here, to make the laser pointer work, there we go. This assumes that everyone is a price taker, no one has market demand, basically a lot of very small actors. Well, you can just sum up the individual demands for N consumers and arrive at the market demand. You graphically will sum this up horizontally. Here's an example. Two people, person A, person B, and these are their demand graphs. You see, person A is not willing to purchase any at all at a price higher than P1 double prime. Person B goes to zero quantity demanded at a slightly higher price, P1 prime. Now, if these two people are the only actors in the market, the only sellers, you would add, graphically, their demand curves horizontally. So, what if the price is above P1 prime? Person A will buy zero, person B will buy zero. Therefore, the market demand above that price is zero. Now, what if the price is between P1 prime and P1 double prime, in between these dotted lines? Person A still won't buy any. Person B will buy some. Therefore, person B's demand, this little segment of the blue line, is the entire market demand. And you see it represented there. This is the same as this. But if the price is below P1 double prime, then both will purchase some. Add them horizontally, and you get this black line. Look at whatever minimum price is represented here. Person A would purchase 20. Person B would purchase 15. Market demand, 35. Pretty straightforward. Okay. The main point of this chapter is elasticity. Now, I assume you did see elasticity, you may even remember it, from principles. The concept is the same. The way we calculate it in intermediate micro is different. First, what is elasticity? Elasticity is a generic term referring to how responsive one thing is to a change in another. For example, the A elasticity of B means how much B changes for a given change in A. Now, the first elasticity you learn about, generally, is the price elasticity of demand. Here. That means this would be like that. It is the effect on demand of non-working computer pens, the effect on demand from a given change in price. Price elasticity of demand is the most common one we talk about. It's the first one we teach, but it's not the only one by a long shot. For example, price elasticity of demand. Now here it says own price. That means if you're talking about demand for apples, the price is the price of apples. This means if there's a price change of so much, how much of a change in demand will there be as a result? How sensitive is demand to price? If the price changes a little, will the quantity demanded change a lot? Maybe if price could change a huge amount and the quantity people want to buy would change hardly at all. These are different examples of price elasticity. In this case, own price elasticity. There are others. The cross price elasticity of demand. It's the same idea, but the price referred to is the price of something else. If the price of apples goes up $1, what will happen to the quantity demanded of oranges? How sensitive are oranges to a change in the price of apples? When things are substitutes or complements, this becomes relevant. Then there is the income elasticity of demand. This asks, if income changes by a certain amount, how much will demand for a thing change? Some things people are going to buy pretty much the same amount, even if their income changes dramatically. Other things are very sensitive to changes in income. And just like in most things, what works for demand works for supply. Own price elasticity of supply. You're making widgets. If the price of widgets goes up 1 unit, how much do you change the quantity you supply? A little bit? A lot? There are others. Okay. Now, when we are looking at elasticity graphically, there we go. Let's see. We can use, we don't, but we could use the slope of the demand curve. Quantity, price, excuse me. Okay, there is a demand curve. At high prices, people don't want to buy many. At low prices, people want to buy a lot. Simple demand. Now, geometrically, the relationship between price and quantity could be represented just by the slope of the curve. And in this case, it's a line, so it'd be really simple. Let me show you another example. Let's say instead of that demand curve, you had this one. It's still a demand curve, but you can see that a very small, alrighty, going to use the mouse again. You can see that a very small, rats. Let me try this one more time. You can see that a very small change in price corresponds to a very large change in quantity. This would be something that had very elastic demand. It's very sensitive to price. On the other hand, you could have a curve like that, where price could change. Sorry about this. Where price, rats, could change a great deal, and quantity would only change a little. This is something that is very insensitive to price, very inelastic demand. And it's just represented by the slope. Now, why don't we use that simple measure of elasticity? It is because it is dependent on units. If you change the price from dollars to yen, well, the number is going to get roughly, as of this recording, roughly 100 times bigger. It'll give you a different elasticity value. If you measure quantity in units or millions of units, the number will change. Even though the behavior isn't changing, people's decisions of what to buy or sell, how many, usually doesn't depend on which currency they're using to pay for it or how people report sales figures in dozens, in hundreds. So just looking at the slope wouldn't work well. Instead, we measure it in the unitless percentage change. So elasticity, and this is lowercase epsilon, usually used for elasticity, is the percent change in quantity, here indicated as x1, that is caused by a percent change in price. If the price goes up 1% and the quantity demanded goes down by 2%, that would be an elasticity of 2. Here's where a comment on an awkwardness is appropriate. The sign. The book talks about this a bit, but I want to reinforce it. When we're talking about, for example, income elasticity of demand, your income goes up. Well, depending on the good, whether it's a normal good, an inferior good, you may end up purchasing more. You also might end up purchasing less. So the sign of the elasticity is ambiguous. So you have to specify. Is it positive, a positive effect on quantity demanded, or a negative effect? Could be either. However, when we're dealing with price elasticity of demand, and we're assuming that all these relationships are well behaved, we don't have to wonder about the direction of the change. Price goes up, quantity will go down. And we're assuming it's not a given good. So when we're dealing with price elasticity, there is no ambiguity about the sign of the change, about the sign of the elasticity, which means that economists traditionally get lazy. We know that for all but bizarre cases, the elasticity is going to be a negative number because price and quantity are going to move in opposite directions. Price goes up, quantity goes down. Price goes down, quantity goes up. But traditionally, since we know the direction of the change, essentially always, when dealing with price elasticity, we drop the sign. It's as if we're always talking about elasticity in absolute value terms. So when I say, let's say there's a good that is very, very sensitive to price changes. A very small change in price causes a huge change in the quantity people buy. Well, we say that's elastic demand. And we would say maybe the elasticity is 3. That's big. What we actually mean, so a 1% change in price causes a 3% change in quantity. But actually, even though we say it this way, it's not quite right, because technically, that would be an elasticity of -3. And if I say the elasticity of this is bigger than that, I mean in absolute value terms. For example, something that was even more elastic, where a 1% change in price caused a 10% change in quantity, I would call that a price elasticity of 10. And I would say the price elasticity of the second thing is bigger than the first thing, even though technically I mean -10, because if the price goes up, quantity is going to go down. And you can see that, well, if you want to be technical about it, and who doesn't, -10 is a smaller number than -3. It's to the left of it on the number line. Just be aware, when we talk about price elasticity of demand, since the direction is not ambiguous, we talk about it just in absolute value terms, and we drop, even in some papers, we just drop the minus sign. Now, when we're dealing with other elasticities, like income elasticity or cross-price elasticity, well, you don't know which way it'll go, so you always include the sign. Just something you gotta know. Okay, now, in principles, I'm pretty sure you saw elasticity, but the way it was calculated then, we call arc elasticity, and it was called the midpoint method. That gives you an approximation. It doesn't give you the exact value. The algebra is ugly, it's awkward, but we have to do it that way because that's the only way to calculate it without using calculus. If you want to know the exact value, we call that the point elasticity. And you need calculus to do that, usually. Arc elasticity gives you the average elasticity over an arc, over a range of demand. Let's see. Arc, price elasticity of demand. We're just going to assume its own unless we say otherwise. Well, it is the percent change in quantity divided by the percent change in price. But you have to use, since you're doing it over an arc, and let's see if I can do this. Okay, that's quantity, that's price. You have 2 points. The old bundle, or the old demand, and the new demand, at the old price and the new price, the old quantity, the new quantity. Well, this formula, the old quantity, the new quantity minus the old quantity, divided by the average of the two quantities, converts it into percentage terms, and you do the same thing for price. It gives you the average over this here we go. It gives you the average over, nope. It gives you the average elasticity over this arc. Very badly drawn. But if you want to know the elasticity, not over this arc, but the elasticity at this exact point, you need to know the slope of the curve at that point. That's a tangent line. Well, that's the derivative. And you convert that into percentage terms this way. The elasticity, it's this formula. But when you take the change all the way down to 0 to an infinitesimal, this becomes, let's see, this becomes, let's see if I can do the math for you here. Let's assume that the formula for quantity is the price is some number A minus B times quantity. Solve for quantity, and you get A minus price over B. Now, I'm going to simplify that algebraically just a bit because it makes the derivative a little more obvious. This is the same as A over B, that's just some constant, minus P times 1 over B. The derivative of that with respect to price is, well, the derivative of a constant, that just goes away. This is a constant times the variable, and there's an implied -1 there. So the derivative is -1 over B. Okay, that is the formula for the slope of the demand curve at any arbitrary point. But, which is this term. But you need to multiply that times price over quantity. So that gives us over B times P over Q. But this is a problem because the elasticity we want to find is a number that represents how much the quantity changes in response to a change in price. Well, so we can't have Q in there. What do we do about that? Well, we have this that describes the relationship between quantity and price. So we can take the right-hand side and plug it in. So the elasticity equals -1 over B times P over that, because that is Q. Little algebra that I don't have space for, and you end up with this, the elasticity. We will get through this semester together somehow. The elasticity equals -P over A minus P. Here I've explicitly included the negative sign because you know that's the direction of result. Okay. So we have that here. That's the formula for the elasticity at any particular price. Now, here is a very, very simple linear demand curve. The elasticity in percentage terms, The elasticity, if we used the first method I discussed, where we just look at the slope of the line, it would be constant across all prices. But we don't use that because that's sensitive to units. When we express it in percentage terms, though, it means that on a linear demand curve, the elasticity in percentage terms will change over different prices. The elasticity at this price is not the same as the elasticity here or here. Why? Well, it's not that the behavior is changing, it's the way we're expressing it. Because we're expressing it in percentage terms, well, think about it down here at a very tiny quantity of X. Well, you have a really big price and a very divided essentially by a very tiny quantity. So if you're looking at it going the other direction, that would imply that a very big change in price, a very small change in price would result in a very big change in quantity. It's because you're dividing by price. Now, the same behavior over here, you're dividing by a bigger number, which means the total elasticity will be smaller. So, the important thing to remember, on a linear demand curve, the elasticity is not constant. Here, it goes to infinity, again, negative infinity, and here it goes to 0. In between, you'll have an elasticity of 1, again, in absolute value terms. We call an elasticity bigger than 1 in absolute value terms, elastic, less than 1, meaning between -1 and 0, inelastic. And if the elasticity is exactly 1, a 1% change in price causes a negative 1% change in quantity. We call that unit elastic. So it's the denominator here that's changing across prices. Now, what would a curve look like if there was constant elasticity? Excuse me. This is a reasonable representation of that. This curve would have the same elasticity at a high price as at a low price. But the slope changes. It's because you're dividing by a different number. Okay, now, one important application of price elasticity is production decisions. If you decide to produce more, to increase output from your company, what happens to total revenue? Well, the answer is it depends. Here, total revenue, the total amount of money coming in, is the quantity you sell times the price you get for each of them. Pretty straightforward. But the law of demand says that all else held equal, if the price goes up, the quantity demanded will go down. Okay, and the reverse relationship holds as well. So if you increase production, quantity goes up, well, price is going to go down if you are the entire market. Well, a bigger Q times a smaller P, what's the net? Is total revenue going to go up or down? That's the kind of thing that would be important to know, wouldn't it? Turns out the answer is it depends on the elasticity. If the price elasticity is small, it's inelastic. The way to think of inelastic is it's the quantity people purchase, it's just not very sensitive to price. So if, for example, you were to increase the price, well, yes, the quantity people will buy will go down. But remember, it's inelastic. People respond to price, just not very much. Price goes up, quantity goes down, but only a little bit. So price times quantity goes up, revenue goes up. However, if there was something that was very sensitive to price, very elastic demand, a small change in price would cause the quantity to change a huge amount. Well, you want to increase the price? You can. Increase the price a little. Your sales will drop like a rock. And price times quantity, your total revenue, will go down. It sometimes gives people a little trouble with the intuition. Here, I'm showing you the result of a change in price. What happens if there's a change in quantity? Well, it works the other way. If you increase, let's assume demand is very elastic, very responsive to price. Well, if you increase, that means a small quantity change, if it's elastic, it means a small price change. It'd be better if I wrote this so you can see it. Okay, elastic. So a small price change causes, just graphically, a big quantity change. Now, if you were changing your price, raise the price just a little, your quantity is going to react a lot. Sales will drop like a rock. But if you're going the other way, let's say you want to, so you're not changing your price, you're changing quantity. If you increase the quantity of output by some amount, what's going to happen to the price? Well, there'll be a very, very small price change. So if you're increasing your quantity of output and demand is elastic, price times quantity would end up being bigger. So here, if demand is elastic, increasing the price will cause total revenue to go down. But increasing the quantity would cause total revenue to go up. That is the core of this chapter. It's just price elasticity that you saw before. The big innovation in this chapter is how to calculate it using calculus, the point elasticity method, rather than the arc elasticity estimate. That's it for today. I will see you next time.